what are we going to do today? I don't even have a great slide for that. I feel that in 2025, in a course that's called Probabilistic Machine Learning, there has to be an introduction to generative models of the modern form, diffusion and flow matching models. So I made a lecture about it, and I was trying to figure out where to put it in this course, so I put it here, right after the Monte Carlo lecture, because there is a nice way to segue into these models from the Monte Carlo perspective. I'll have to include a few caveats, a few like parental notices, advance warnings at various points across this lecture today. The first one is it's the first time I'm doing this, so it may be a bit rough around the edges. Also, I'm absolutely not an expert on this generative modeling. I've just read a lot of papers. Thankfully, they were provided by me by smart PhD students like Jonathan, who's sitting there in the back. Looking forward to see what came out of this process of him sending me papers. And he'll probably occasionally, good that he's sitting in the back so you can't see him occasionally going when I'm saying something wrong. Also, this is of course a very rapidly evolving field, and it's just a single lecture. So what we'll be able to do is just to get a first glimpse at how these methods work, where they come from, what kind of interesting aspects are about them, and I'll say more about that towards the end of the class as well. So, and there are many different ways of approaching this question of generative models. In fact, it's connected to many, many different model classes across machine learning. And I'm just going to take one particular path into this maze that is generative modeling, and that's based on the stuff we talked about on Tuesday, Markov chain Monte Carlo. So, quick recap. Last lecture, I introduced various methods. Let me go back to this picture. That iteratively move around the input space of a probability density function to produce samples from a distribution. And by iteratively, I mean that they follow a Markov chain. So at every point in time, they evaluate density at one particular point and then do something local that depends on where they currently are. I showed you various such algorithms. Here's another one that I'm going to introduce in a second, that's called Langevin Monte Carlo. Actually, it's a variant of Langevin Monte Carlo, which is somehow related vaguely to Hamiltonian Monte Carlo, the method that I mentioned at the end of last week's lecture. And we noticed that these algorithms, although they are sort of very concrete, graspable algorithms that asymptotically are actually theoretically guaranteed to draw from the true distribution, have all sorts of practical challenges. And one of them, a very problematic one for complicated distributions, especially high-dimensional ones, is that they really struggle with non-concavity of the log probability density. So that's a technical description. Maybe to put it a bit more simplistically, they struggle with distributions like this one, which are multimodal, so which have sort of islands of probability, and then those islands are separated from each other. So here you see that I've been running this algorithm for quite a while already. Now you've been watching it as we go, and you can see that this algorithm has managed to actually discover both of these modes, but it then spends a lot of time in one of these modes, and actually it takes a really long time to get to one of the other ones. Now we might just get lucky. No, we didn't get lucky, we went back down here. And so far, this algorithm has completely ignored this one over here. It just hasn't discovered that there is this island yet. Right? So lucky me that this worked, because it doesn't always work. So here we, okay, now we're in the other one again. And so this is a two-dimensional space. So this is arguably a very simple problem. In higher dimensions, this gets much, much, much harder. And the probability of getting stuck increases exponentially with the dimensionality if the distance remains the same in each dimension. So this is one of the problems that we're going to address today. And we'll discover that we can address this problem in a super elegant way that, as a sort of almost as a side result, will also address a completely different problem of Markov chain Monte Carlo methods, which is that they need access to this unnormalized probability density. And in fields like probabilistic programming, where you write a program that defines probability measures, that may not be a problem. You may be able to evaluate these densities up to normalization. But in empirical settings where we have samples drawn from some distribution, we might not have this P, and we would like to learn it in some form. And we'll discover today that we can do both and end up with a tractable algorithm that can sample for very complicated manifolds of probability distributions living on manifolds that are only accessible to us through samples. So for example, natural images, and then we can build algorithms that draw from the set of natural images. And of course, you know all of these algorithms because you've probably played with them. So let's talk for a second about Langevin Monte Carlo. So how does this work? Here's the actual algorithm. Langevin Monte Carlo is the following one-liner Markov chain Monte Carlo method. So our goal is to draw from a probability density function P of x. We assume that we have access to the score, so that's the gradient of the log of P. If we think of the log of P, if we think of P as e to the minus energy, then this is minus the gradient of the energy. That's called the score. And so the algorithm now works as follows. We initialize the method by drawing an initial sample x0. We draw that from some whatever distribution. It just has to have full support. We just draw somewhere. And then we forget about this and just iteratively draw from the following Markov chain, which draws a new sample by adding to the old sample a constant epsilon times the score plus square root of 2 epsilon times a uniform standard Gaussian random variable. So I keep saying uniform. A standard Gaussian random variable. So there is no proof on this slide for why this works, and I'll just omit it. But maybe here's an intuition for how this works. Remember Hamiltonian Monte Carlo? There we were also following the score. So the first thought you might have is, so the score points in the direction of higher probability, right? So this algorithm is moving towards regions of higher probability. But of course, we don't just want to follow this deterministically, because if we do this, then we're building an optimization method rather than a sampling method, right? So it'll just move to a mode and then get stuck there. So to not get stuck in the mode, we have to add some noise, some stochastic step, that's this one, such that will move around the distribution. Another question is just how large does the noise have to be relative to the gradient so that we end up in the right distribution, and it just happens to be exactly this value. So an epsilon here and a square root of 2 times epsilon here. There is actually a way to motivate this from the Hamiltonian Monte Carlo perspective as a very specific form of very naive solution to an ordinary differential equation. You'll remember that to draw Hamiltonian Monte Carlo steps, we solve an ordinary differential equation that is in phase space, right, where the particle has mass and therefore momentum and moves in this direction, and we solve this ODE in every step of the method by randomly initializing the momentum and then solving the ODE. This is a very, very basic way of doing this. We just solve the ODE in a single Euler step, basically. Okay, good. So this kind of method is actually sometimes used in interesting applications. For example, it's a classic method used in Bayesian deep learning as an alternative to Laplace approximations. When I did Bayesian deep learning, I talked about Laplace approximations. And you'll remember some of you asked, well, is this the only thing we can do to be Bayesian? I said, no, you can also use Monte Carlo methods. This is a common way to do Bayesian deep learning with Monte Carlo. Why? Because here this score is literally just the gradient of the loss. So that's what you use for SGD, right? And so there's a very nice idea here that you can do gradient descent on a deep neural network and just add a little bit of noise, and that's it. And this noise involves the learning rate here, right? This is like the learning rate of stochastic gradient descent, and you just add a little bit of the right amount of noise, and then asymptotically you'll get not an optimizer that converges to a trained neural network, but some kind of diffusion process that moves around the posterior, and then you can call this samples from the posterior of the neural network. But this algorithm has exactly this problem that I also just visualized to you, and here's another picture of this that I quickly made. Here you see 3 of these Markov chain Monte Carlo chains, Markov chains, a red one, a gray one, a mustard colored one. There's a multimodal distribution here, and you can see that 2 of them end up in this region and 1 ends up in this region, and then they're sort of stuck there. Actually, one of them ends up here, one of them ends up there, and the other one, the gray one, happens to manage to make the cross from one to the other. This is a two-dimensional problem. Again, in high dimensions, these algorithms can get stuck in one mode for a very, very long time. And then it's also very difficult to notice that that's the case. You need advanced diagnostics to do something about this. And so, yeah, that's a problem. And in fact, there's theory. So if you click on these links, you can find theory papers that highlight that this algorithm can converge very slowly if the distribution is multimodal, and it can converge very fast if the distribution is log concave. So if the score is the gradient of a concave function. So here comes the first idea, super cool idea that is down to, and on the next slide I forgot the citation, but it's then one slide later, a famous member of the old-style machine learning community, Aapo Hyvarinen from Finland. And he made the following observation. He said, what if we convolve the probability distribution for x with a Gaussian? So another way of phrasing this is to say, if we take the x from which we want to draw, the random variable that comes from a probability distribution p of x from which we want to draw, and we add some Gaussian noise to it. So we're going to write a new random variable, y, which is given by alpha times x, where alpha is some positive constant less than 1, larger than 0, plus sigma times z, whereas sigma is just some other constant. Then what's going to happen is that the conditional distribution, sort of by definition of y given x, of course, is a Gaussian. I mean, it's just obvious from here because linear transformations of a Gaussian are a Gaussian, right? Or actually, not just that. We're just adding something to a Gaussian. Yeah? So it's really just Gaussian conditional distribution, and the marginal distribution of y will be a convolution of this Gaussian with p of x. So therefore, the score of the distribution of y, not of x, will be, here's like a 3-line derivation, it'll be constant times the gradient of the convolution of a Gaussian, of a convolution of p of x with a Gaussian. So here's a picture for this. In gray in the background, you see this, our by now much loved 2 moons distribution. And what I've done is I've taken every single one of these gray points and added a bit of this kind of Gaussian transformation by setting alpha to 0.95 and sigma to 0.2. Now you can see that this distribution, the red dots, are a lot less peaky, right? They are much more broad and smooth. And that's a fundamental property of Gaussians, that convolving with a Gaussian makes a distribution more convex. You've probably seen this in various different other domains. Maybe you've done a computer vision course or a graphische Datenverarbeitung course by Hennig or somewhere else, and you know that Gaussian filters applied to an image make it smoother. Instead of old-style image processing tools, Gaussian smoothing, you get a smoother image that looks more blurry. That's exactly what we're doing here. So now Aapo Hyvarinen says, one could come up with a variant of Langevin Monte Carlo that takes 2 steps. The first one is, to draw from p of x, we first convolve the density of x with a Gaussian here. Now we have a much simpler distribution where it's much more likely that Langevin Monte Carlo will work well, because there's, you could argue that there is a lot less islands now. This is all one well-connected distribution. Then we take one of these Langevin steps, and then what do we do? So now here's the interesting bit, right? Now we have to go back down. So this is called jump Langevin sampling. So you first add Gaussian noise, then you do a Monte Carlo step, Langevin step, and now you have to go back down towards x. And that means we have to reverse this process. We have to go back from y to x. How do we do that? That's actually something you can guess without having read the paper, which is from 29. Well, actually, it's from 2005, actually, by the way. Maybe I'll give you a hint. Clearly, the task we have here is that we have to infer what x was if we have a new y. How do you do inference? Bayes theorem. Thank you very much. First point in your exam, done, right? So you're looking for an unknown quantity given something we know, so we need to apply Bayes theorem. We're going to compute something like an expected value of x under the posterior for x given y. So let's see if we can do that. So here is actually the link. This is an updated version of this paper that's much clearer to read by someone else, actually, Saremi and Hyvärinen. There he is again, Apo. The original paper is from 2005. I'm citing it on the last slide. In 2019, here they wrote an updated version. So here is just, in gray, you just see repeated from above what I just said so that you can refer to it. Now, our goal is going to be, if someone gives you y, and they've done a Monte Carlo step on y, let's estimate what x was. Okay, so to do that, here's the exact derivation as it is in this paper, line by line, literally even copying the sentences afterwards. So they say, let's write down the gradient of the likelihood for y given x. So we're going to do Bayesian inference, right? So there'll be a likelihood in there, p of y given x, and that's the easy distribution. So that's the Gaussian likelihood that we basically constructed for ourselves. So the gradient of a Gaussian is, well, it's it's up here, right? If you look at this, this is even wrong. Man, I should have put an alpha here, right? There's of course an alpha in front of the x. Sorry about that. But if you think of what the gradient of this is with respect to y, you may be able to convince yourself that it's alpha times x minus y times the likelihood, right? Because there's an exponential here. So if we take a derivative, we get the exponential again times an inner derivative. Okay. Everyone following so far? Good. Now we multiply by p of x on both sides, which is fine because p of x is assumed to be a non-zero probability density, which we assume to exist. So we can just multiply by it. And then we integrate on both sides against x. So we have multiplied by p of x. Now I'm going to integrate against the x. And now I use the product and the sum rule. So p of y given x times p of x is p of y comma x. And then if you integrate with respect to x, you get p of y. And the integral and the derivative commute, so we can just write dp of y dy. And on the right-hand side, we also get p of y given x times p of x is p of y comma x. And then we can integrate against x. And what we get here is that in the term with the x, we get an expected value of x under p of x given y minus, well, y, if an integral against x is just, right, the integral against x is just a probability distribution, it's just 1, so y times p of y. Now we divide by the p of y to put it on the other side, and we realize that if you get, if you get 1 over p of y dp of y dy, that's the same as the log of p of y dy. Everyone still following? No? So the derivative of the logarithm of p is 1 over p times the derivative, what? No. The derivative of p. Oh, that's a mistake. Can I just directly correct this? Oops. Sorry. Too many automations happening at the same time. Let's see. And then there was also a mistake up there. So we need an alpha in the, that's when I do a lecture for the first time. So now we have an alpha up there. Good. Now maybe you've had enough time to think about this. Does it make sense now? No one is nodding, so I've lost you already. So where are you stuck? Can someone ask a question? Yes? So the algorithm we're going to build is, so the question is, why again are we doing all of this? That's a great question. So we started with an algorithm that takes a p of x and samples from it. We discovered that this algorithm had a problem. We said, it would be much nicer if you could sample from y, p of y is x plus Gaussian noise, because that distribution is much easier to sample from. But we don't want to sample from p of y, we want to sample from p of x. So the algorithm is going to be start with a sample from X, add some noise, so now we have something Y. In Y, do the Monte Carlo step, the Markov chain Monte Carlo step, because that's easier to do. And then we have to go back down to the space on X's. How do we do that? Well, we estimate what the X would be that corresponds to this Y. So we're going to compute an expected value of X, given that we now have a new Y. So we need to compute an expected value of X under Y. Here, there it is. This is the thing we're interested in. And to get to that, so at the end of the slide, right, we have an expression for it. We do this derivation. So we start with the likelihood, which is explicitly available because it's a Gaussian. We compute a derivative, which is analytically possible because it's a Gaussian. We integrate on both sides, which just uses properties of probability distributions, sum and product rule. Then we do one of the integrals analytically, and now on the right-hand side, we have the thing we're looking for, the expected value of X under X given Y. And now we just have to rearrange the equations to get something we can read. And we notice that there's a P of Y here, so we divide by P of Y, and then we see that we have over here something that looks like this, which is equal to the derivative of the log of P of Y. And that is the score, right? That's this thing that we've encountered in previous algorithms. Okay, now a few people are nodding. Are you following now? Good, much better. Great. So we can rearrange this equation, and we find that our expected value for X under, like given that we have Y, is this. This is an estimation rule that says to estimate what X was, take the Y that you got after like adding some noise, and look at the score of the marginal of Y, which is this easier distribution, right, which is this Gaussian convolution of the P of X, and add a bit of a gradient step, basically, right? So to go towards, this contains some information about where the X's was, because it's this smoothed out version of P of X. And there's a sigma in here, which is the amount of noise. If there's a high noise, if a lot has been done to X to get to Y, we need to correct a lot. And if nothing has been done to X to get to Y, then sigma is 0, and we can just use our Y, well, divide by alpha, to get back to X, right? So that would be easy, but like, obviously we want some noise, because otherwise it's not more Gaussian, and then this entire thing makes no sense. So the question is going to be, how large should we choose sigma? Well, a possible answer to that, one way to derive, and this is my own little trick, is to redo this entire derivation from Apo's paper, which I did on a piece of paper, and I hope I got it right, which is basically the same trick again, just with a second derivative. And then you get also an expression for the variance of this distribution. I've done that here. I've left out the derivation. Up here, you see what we just had on the previous slide. That's our estimation rule for X given Y. And then we can estimate basically the error of our estimate, the variance of this estimate. And you can see that this variance is, also again, there's an alpha. And now we get something in sigma to the 4 times the Hessian of the log of P. So that's something like, you know, Hessians we've seen before in Laplace approximations and the Fisher information and so on, plus sigma squared. And now that tells us that there is a trade-off to be struck. Let's see if I can make you follow on this. So given that we are in this framework of an algorithm that takes a single sample step, so to do Markov chain Monte Carlo, we are in X space, we add some Gaussian noise, we take a Langevin step, we estimate X again, and then we continue, right? Add some noise, take a Langevin step, estimate X again. Given that we have that setting, our question could be, how should we choose sigma? Well, if we choose sigma very large, then the good thing is going to be that the distribution of Y will be almost Gaussian. So let's go back to this picture I showed you. If we set sigma large, then this distribution will basically be a standard Gaussian. It'll just be a big, like, blob of Gaussian noise. Well, actually not standard Gaussian, depending on how we set alpha, right? So in the extreme case, if we set alpha to 0, and we set sigma to 1, then we just get a Gaussian sample, right? Then everything is just, it's just a standard Gaussian sample. So is that going to be fine? No, of course this can't work. Why? Because we're dividing by alpha, first of all, so we can't divide by 0. So alpha will have to be something non-zero. But also, if we set sigma square very large, then we'll have to make a big correction to get back to X. And that correction will carry a large error, because the sigma to the 4 will enter drastically. Right? And we'll be very uncertain about what the correct X actually was. So on the other hand, if we set sigma very small, then Well, an interesting observation is, well, if your sigma is very, very small, then we can basically ignore this term because the square of something very small is something even smaller, and we basically just get sigma square. And that tells us that, so now we're effectively just back to a Gaussian distribution for x. We just take more or less y corrected by alpha, and our error is a Gaussian error pretty much. You can actually continue this derivation then, and you'll find that all of these higher order terms in derivatives all cancel out, and your posterior over x given y is approximately a Gaussian because you've just added a tiny bit of Gaussian noise. So that seems like a good thing, but it doesn't gain us much because then the distribution of y will inherit all the problems from the p of x, right? And it'll still be this very multimodal distribution that doesn't look like a Gaussian at all, and all the problems that we had in the previous case are just there again. Question? Did I say sampling early?
That's on the slide. Do you mean honest or like?
Oh, easy. It's easy. My autocorrect directly. Aha, that's the problem with typing with an LLM switched on. Yeah, so it's easy. Sampling is easy because y is nearly Gaussian and it has high variance in x. I'll just correct that. Then sampling is easy. There we go. So, okay, did everyone get that? Because that's a key observation. So now, right, if we wanted to use this algorithm, we could say, okay, let's just find some sigma in between that makes the distribution in y a bit easier to sample from, and also we can still estimate x well. What other thing could we do? Maybe someone can already guess what the trick is going to be. There's a very computer sciencey answer out of this problem, I would say. Well, maybe it's also a mathematical answer out of this problem. I don't know. That actually took, I think, quite a while for people to figure out. And maybe the first paper that really made this very clear was in 2020. Does someone want to guess? Yes. So you're thinking of an optimization problem. So we'll play around with the sigma choices up until the Hessian of p of y can be shown to be convex. Interesting idea. Yeah? So that would be like a tuning process for sigma. Yeah. Another idea? Yes, we just do it a few times. If each one of these steps requires sigma to be small, and then when you do a small step, there isn't much to correct, how about we just do a lot of these steps? And instead of going up once, doing a sample, and then projecting back down, we project up and up and up and up and up and up and up, do a sampling step, and then go down, 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 down. That will increase the computational cost, because we'll have to do it more than once. But every single step will be easier. And if we do this a lot, then we can make sigma very small and make a sequence of corrections, where each correction is a good one, because sigma is small. And nothing keeps us from doing that for a long time until this is effectively a Gaussian distribution. And that's the idea of, well, denoising diffusion models. And here's a first widely cited paper on this from 2020. There's actually, interestingly, a group of people, largely in California, now in different companies that emerged from academic research labs over the years that have completely driven this field. Something like 5, 6, 7 people that you can find as co-authors on all of these papers. And interestingly, sometimes halfway through, let's say, go from one paper to another, their affiliation changes from one company to another because they've been hired. You can sort of see this happening in real time almost. So here's this paper from Ho et al. At the NeurIPS in 2020 that suggests a Markov chain of transitions. So we say to create something that is very Gaussian, we'll just do a lot of individual steps where we go from one time step to the next by adding Gaussian noise to the previous iterate in this particular form. So you start with a sample from p of from P0 of x, the original distribution on x. And then we introduce a variable t that you can think of as time, but it's not the time of your video, it's some other space that we now also call time, where along this time dimension, we iteratively add Gaussian noise in a sequential fashion, in a Markov chain fashion. If we do that, then every local step is a small Gaussian perturbation. And therefore, the projection step backwards is approximately a Gaussian estimate again, because of the previous slide, right? So if sigma is very small, then this correction is very small. We effectively get something that's almost Gaussian as the backward distribution to estimate the previous x. And so we can say there is probably some backward process that gets us backwards from the final time to the original x0 that locally looks like a bunch of Gaussian corrections to move from xt minus 1, sorry, from xt to xt minus 1. The slide is right, I just said it the wrong way around. And the only thing we need to figure out is how to set those two parameters of our estimation to get back. So in the previous slide, we actually had the same structure. We just didn't divide it out like this, and we just thought of a single step, right? So I could have rewritten this to say, oh, we're going to do a backward step where we draw an estimate for x by computing this, calling this the mean of a Gaussian estimate, and then computing this and calling that the Hessian, calling that the variance of our Gaussian estimate. Let's draw from that distribution, and then we have an estimate for x. But now we're not going to do it once, we're going to do it over and over and over again. And because the sigmas will be very small, the noise will be very small, hopefully that will work very well. Yes?
Is this Q the same thing as the P of y?
Which PU?
The Q.
The Q. Ah, Q. No. Okay, so this Q is sort of the typical nomenclature for an approximate distribution or something you induce, you impose. So we're going to say that we have an initial x0 that comes from P. And now we create a sequence of distributions Q that come from this Markov chain. But the symbol P will be overloaded over and over and over again in the next slides. So also, the notation changes because people have introduced lots of parameterizations for the resulting objects. So the notation will be a little bit all over the place. And this p theta is a new p again, right? This is the original, sorry, no, that's not even that, right? That's just the final distribution, the induced distribution on the final x at time capital T after we start from p of x0 and then add lots of Gaussian noise. And this theta has this index theta to suggest that we'll need to find out how to set these two objects. If we have those, then we can go backwards in time. And now there's one more idea that comes from a follow-up paper with a bit of overlap in the authors from 2021 at iClear, where the author suggests actually there is a smarter way of doing this that allows us to parameterize the distribution more elegantly. And it requires us to make a little change to this idea that is a bit more complicated, namely that we're going to assume that it's not actually a Markov chain, but it's a chain of distributions that all jointly depend on x0. That's just a choice they have to make, that they found they had to make to get to an interesting parameterization. And it works as follows. It's actually best understood to just look at the math, I think. They say to produce this sequence of noised samples, we start with, we invent distributions like this. So basically, this is the same structure as on the previous slide, but now every one of these conditional distributions is allowed to depend on the initial x0. So we sort of keep information around for the original sample that everything came from at the start across the entire chain. And locally, for these both for the final term and for the individual terms, we make this choice. So these are still Gaussians, right? So we still say the new iterate comes from a Gaussian. Made that did this wrong. I think this is a this should be t and t minus 1, I think. I might be confused. But the important structural idea is that this forward process is a Gaussian with a scalar in front of xt, and then a correction that uses x0, that makes this distribution depend on x0. And this specific parameterization with a parameter alpha and a lot of square roots and a parameter sigma floating around is chosen such that you can then show by a proof of induction, that is like not something you can just read off, that the marginal distribution over xt, every individual xt, given x0, is a Gaussian with a mean given by the square root of alpha of x0, so alpha is some parameter that you get to choose, and the variance is 1 minus alpha times standard Gaussian. Why this emerges from this, you can't just read off. You have to read the appendix of this paper that I'm citing up there. And it's an inductive proof, so they just say if this is true at time step t, it's also true at time step t plus 1. And then it's true at time step 0, and therefore it works. So why is this interesting? Well, because we now get to choose what the alpha t is. So basically now if you have a design space of a noising process, alpha t, that you can sort of play with. And that turns out to be actually quite powerful, because you can then say, well, we'll see actually in a second what you can do with this, because I'll show you an example before the break. So here's the picture for this. They actually also point out if this is true under this, no, this is actually correct what I wrote here, because then the forward process, this thing, so the q of xt given xt minus 1 and x0 can be written like this, obviously by Bayes' theorem, and it turns out that that's then actually a Gaussian, right? Because here this, by definition, so this is inductively a Gaussian, and this is a Gaussian distribution by definition, and this is also a Gaussian distribution, and therefore the whole thing is a Gaussian distribution. Doesn't matter though. So what this allows us to do is to define an object called a diffusion process that takes in such a schedule alpha and then operates on arbitrary initial values x0. And I've actually implemented this together with Jonathan. Here's the first half of it, and I'll show you the code for it in a second, also over in a Jupyter notebook. But let me first tell you what's happening here. So we can now say, let's define something called the diffusion process that contains such a schedule alpha. And if we have such a schedule, we can make something called a forward process. This is a function that takes in, obviously, a random number generator, because we're apparently using random numbers, then an initial value x0, and a time t up to which we're supposed to simulate. And now what we're going to do is we'll draw a standard Gaussian random variable and compute xt to come from this distribution. Namely, we set it to the square root of alpha times x0 plus the square root of 1 minus alpha times this standard Gaussian random number. Why the square root? Because that's the standard deviation, right? So notice that this is a single step. We do not have to do the intermediate time steps. There's no reason to think about the t's, the discrete steps between 0 and the t that we want to simulate to. We can do this directly in a single step because of this marginal property that it has this distribution. Right? There's no need to instantiate the steps in between. In fact, you can think of this as a continuous function that just takes in a t and produces a sample. And now people choose various scales for alpha. One that is apparently popular, I hear from Jonathan, is something like the cosine of time times pi over a little bit more than 2. I discovered works well. So not exactly 2, because if we go to 2, then at time t1, this would go to 0, and we would be at an exact Gaussian. That would somehow be nice, but also it'll make a lot of gradients very unstable. So we'll do something that almost goes to 0, and then this process will, at time t, produce a sample that is almost an exact draw from a standard Gaussian, so a Gaussian with mean 0 and variance 1. And in between, it'll produce an interpolation between the original data, x, and this full white Gaussian noise. So before we go into the break, I want to show you the code for this, because I have like we made a little visualization for this. This is also on Beat Up Jupyter Hub. So what I do here is the usual stuff to define a bunch of things, and here's this diffusion process. This is the thing that you just saw on the slide. And then there's something else called the backward process, which you can already think about why we will need that. We'll define that after the break. I'll just define that. Now here comes an alpha schedule. I use this particular one that I had on the previous slide. Then I create such an object diffusion process, and that allows me now to produce samples. So here on the left, you see the samples at time t from my standard 2 moons data set again. And on the right, I just show you where we are in the space of what the mean of this distribution is, and, well, conditional distribution given x0, and what the standard deviation is. You following? Some people are nodding. Now I have a slider here, and I can click on that, hopefully, and move it to the right. And you'll see that with increasing t, these samples look increasingly like a Gaussian. Right? And as we go towards 1, they are effectively draws from a standard Gaussian distribution with mean 0 and variance 1, more or less. And we get a continuous interpolation between those. And we get to choose how we get from the original data to the Gaussian. And it turns out it's convenient to start with something that first for a while stays close to the true data, because that gives us sort of more time to keep around the structure of the original data for a bit longer, because it'll become important when we go back, and then speed up to rapidly go towards a Gaussian so that we asymptotically arrive at a Gaussian. So now what we would like to do, of course, is the opposite thing. We'd now like to say, let's draw from a Gaussian. For that, we don't even need to do Markov chain Monte Carlo, right? We can just draw from a standard Gaussian in a single step, completely independent of each other. So we pick any one of these red points, and we want to go back towards the original distribution. So now we'll just need to do the tedious math to figure out how to do that. That'll be the task for after the break. And then hopefully, I mean, here obviously I'm just simulating because I have access to the original thing. So we'll need to write some extra code that does that without knowing what the forward process was. Because then we can do it not just for these red dots, which come from the original data sets, but we can also do it for any other arbitrary sample from a Gaussian distribution. Good. With that, any immediate questions? No? Everyone is waiting for the break. Then let's get started, and I'll, oops. No. And I will see you in 5 minutes. Okay, so maybe to, there was a question in the break that really helped me also, maybe like reminded me that I should maybe like quickly recap the story again. So my argument was, and I said at the beginning, there's many ways of getting towards these algorithms. I'm taking the route from Monte Carlo. There's another approach, for example, from classic generative methods like variational autoencoders, which I would find at this point in the lecture harder to introduce. So I'm not doing that. I'm talking about sampling. And let me just sort of recap the story again. We said, so there is this class of sampling algorithms, Markov chain Monte Carlo methods. They don't even have to be Langevin. It could be anything. It could be Hamiltonian Monte Carlo. It could even be Metropolis Hastings, your basic class of algorithms. They all have this problem that they get stuck in multimodal distributions. So if you have a distribution that has a mode here and one there, then the algorithm can take a long time to get from there to there. Actually, that's not just a problem with multimodal distributions. It's also a problem with distributions that lie on some kind of manifold. If you have a very thin, long distribution, then such an algorithm can take a very long time to get from one end of the distribution to the other, and that's what you need as the sort of free path length to get a single independent sample, approximately. So the observation by people like Apo Hyvärinen is, well, if we would take this distribution and we would convolve it with a Gaussian, so that's thinking of taking a sample and adding Gaussian noise, then the distribution would become smoother because convolution with a Gaussian makes everything more blurry. And then the algorithm could work more easily. Right? And whatever our Monte Carlo method is, Hamiltonian, Langevin, Metropolis Hastings, it would work better. But we don't want to sample from this smooth Gaussian distribution. We want to sample from the original distribution. So we need a fancy way to get back to the original distribution. And we found how to do that sort of in our best guess way for a single step. So if you only take a single Gaussian noise step forward, then this is your best guess backward in a sort of moment matching sense. But we found that if we do that, that's sort of dangerous because the larger the noises we add, the worse this estimate gets, right? We become more and more uncertain about what the original X is. So now the cool, like, new idea from 2020 is to say, let's just do this many times. We start with this distribution on X, then we add a little bit of noise, a little bit of noise, a little bit of noise, and we just do this for a very long time over, let's say, 10,000 steps. And then we have something that's effectively, asymptotically, just a Gaussian distribution. So if we go to the value of t where alpha is 0, then we effectively have a standard Gaussian distribution. And we just have 10,000 steps in between that where every individual step might actually be quite tractable and quite good. And they will take us back to the original axis. So what we just did before the break was we used this formulation, which is this iterative step that marginally produces this very simple parameterizable schedule, and used it to produce samples that effectively come from a Gaussian. If we have such a process that gets us all the way to a Gaussian, then we don't even need Markov chain Monte Carlo anymore. We can just use naive sampling. We just draw individual samples from a Gaussian. We can do that completely independently of each other. And we just call this magic backward process that gets us back down. And then every single individual completely independent Gaussian sample will get us to one completely independent correct sample from the distribution X that we want to sample from. And that sounds almost like magic, but so far we haven't thought about how to do this backward thing, right? So now the name of the game will be to figure out how to do this backward process. Yeah, and it turns out that that actually works, and that's how all these generative, well, more or less how all these generative processes work that you now call, DALI or Imogen or whatever, or Flux. So how does this work? Well, it's going to be the following idea. Look at this slide again. So remember that we had this definition of the marginal process was associated with this definition for the backward process. And now check, the slide is actually correct. I didn't do it the wrong way around. So this is the distribution for t minus 1 given t, index t minus 1. And it contains, it's a Gaussian for t minus 1. And what does it contain in the mean? It contains, okay, this alpha schedule times the old x, which we have, so we can follow that, plus 1 minus alpha or phi. Okay, we set sigma to whatever. This can be anything, actually. Times xt minus O. So here is our problem. There is an x0 in this equation. And x0 is the whole thing we don't know, right? So we need to guess what x0 was to be able to do this process. So the entire task has been reduced to we need to estimate x0 at every single step of the algorithm, and then keep updating this estimate as we go. If we can plug something in here, then the whole rest is well defined and we can just follow it. So that's how this is going to work. So this slide says this again. So look at the previous slide, look at this distribution, which we just looked at. This contains x0. So we're going to replace x0 with our current best guess. And that current best guess is, now I have to go, sorry that I keep jumping around the slides. I go back higher up, just so that you know where to look. Right? Here, that was our best guess for x0, this line. Right? It's the current, that will be our xt, right? Our current estimate, our current noisy version of x. It's the same alpha here, plus, and there is the score. So there's a new notation now that comes from the corresponding paper, it's this ICLR 2021 paper, where they call this estimate this. They say this is our approximate estimate for x0. It's 1 over the square root of alpha t being this schedule for a decay towards 0 mean, times 1 minus, and here this is an approximation to the score, which we can read off from the previous slide to be xt, so my current xt that I have in hand, minus square root of alpha times x0. So that's where implicitly our estimate for x0 is in there. Right? So we, instead of like asking what x0 is, we can ask for an estimate of the score of the distribution. And actually, this particular way of writing things is particularly interesting because it involves this, like it basically reduces the problem or rewrites the problem into estimating this function epsilon of some parameters theta, which is, if you read this off from here, is actually the noise term that got us from x0 to xt. And this is something that tends to be super confusing the first time you see this. So I'll like mention this again on I'll do the plot again in a second, but let's first look at the resulting equation. So rearranging everything again, we find that our estimate for xt minus 1 is our current mean estimate. So that's this long thing here and then some noise. So this mean estimate is, if we reparameterize it in this way, something with current alpha t minus 1 and alpha t times a distance between xt, or a correction to xt that involves this estimate for the noise. And we can interpret that as a prediction for what the original x0 was. So that's like saying xt minus 1 is square root of alpha t minus 1 times the original x0, it's just a rearrangement of the prediction, plus, so to get from xt to xt minus 1, you first go to alpha 0, and then from alpha 0, you go back along the noise towards xt, and that noise is just going to be a tiny bit less than what you had to get to t minus to get to t minus 1 than instead than you had to do to get to xt, and then there'll be an extra noise term sigma, and that sigma will just be the local final last step at time t that adds this tiny little bit of Gaussian correction. And here we now actually get to choose how to pick this sigma. This will be true for every sigma. In fact, it's arguably even true for sigma equal to 0, but then it's like not, well, actually it's not true anymore because then it's not a diffusion process anymore. But there's a weird technical thing that apparently in such backward models, people often set this then to 0, even though it's not really proper if you think about the forward process. But it's something infinitesimal, so people just set it to 0. Yes? Yeah, so, okay, so your question is, if every step we do has a small error, why don't they add up to make a big error? And that's a good question, actually. So it just happens to be the case that they don't add up to a big error if we estimate this thing correctly. So they add up in such a way that it actually just works. I don't have a much better answer than that. But I mean, maybe one short answer is that this process would even work for a single step, right? In principle, it's still well defined for a non-infinitesimal big step, and even works there, just with a somewhat non-trivial error. And it just happens to be the case that the error gets smaller and smaller as we go to smaller steps. And so, okay, so here is, maybe this is really confusing, but also, maybe the best way to think about this is from this picture. One way to think about this backward process is to say, so what I could do is, I show you lots and lots of instantiations like this. So we start over and over and over again by picking a sample from the original distribution. That's this grayish thing in the background, right? And I never actually tell you the original x0. So I never tell you where this, what this distribution over the x0s was. But instead, I do something else. I give you, at time t, now it's 0.56, a sample, this one, and then I tell you what the noise vector was that got you from the original sample there, right? So if you have that, then you can reconstruct the original x0. You just subtract the noise. That's it. So from that perspective, that's the same thing as telling you the original x0. But it turns out to be a little bit easier to learn to say, I just give you pairs of the final point and the noise that got us there. So if maybe just to make this clear, this might clear up a bit of a confusion. If I told you the original x0 and the noise that I added to it, then that noise being added to it would be boring, right? That wouldn't be interesting at all because it's independent. The noise added to x0 is independent of x0. But if I give you xt and the noise that led me there, then that's interesting because xt contains, together with the noise, information about the original x0. So our learning task will be to say, if I tell you where I am in x space, tell me what the noise was that got me there. And that noise will amount to some vector field of directions that point back towards the true data. Does that make mental sense? Some people are nodding. Okay, good. So we're going to do exactly that. So here's the math for this. We're going to learn a function, epsilon of theta, a model that is trained to learn the noise between a produced sample and the original x0 that produced it. So that is a way of learning a vector field that points backwards from any xt towards the original x0. And it'll learn arrows that point towards the original data at every time step. And here's an implementation for this as a loss function. So if someone gives you some deep neural network that produces as an output things that you can think of as a vector field, so in this case it's a function that takes in a noise. So a noise is sorry, not a noise. That takes in a current state. So that's a two-dimensional distribution. And if it turns arrows in two-dimensional space, then if I take such a model, then I can define a loss function that takes in a training point, just a second, from an original data set, and then does the diffusion process, the thing that we just defined before the break. And then it does the following. It uses the diffusion process to ask for a sample from the forward process. That says, please give me an example of where you might end up under your noise process if you start at the original point x0. The diffusion process will make such a noise. It'll say, then I'll end up over here. And now I ask my deep neural network, given that I'm here, what do you think the direction is towards x0? And the network says, I think it's there. And you say, no, you're wrong by this much. Make that smaller. Now gradient descent will make the vectors point in this direction. And over time, this model will learn a function that maps from a three-dimensional space, namely x1, x2, and time, to a two-dimensional vector, which is the local at time t, direction backwards towards the original data. Question? Two questions. Yeah, maybe let's start at the back. Xt is Gaussian distributed when conditioned on x0. The marginal distribution of x of t is not Gaussian. But you get to xt by taking x0 and adding Gaussian noise. Next question? Yeah.
That's why we can't just reuse what we already know about the distribution. So that's why you do it for the sample.
The question is, what do we know about the distribution? So maybe your question is, why do we learn the noise? And here I have to say I haven't really found a good like clean one-line explanation yet. Maybe if you read some of the papers that I have on the last slide, you might find some good one. Okay, maybe one way that a very vague answer that I can give is that this vector field will be, well, maybe it's intuitively more regular because it's just a set of arrows that all point towards the original data across time, and they smoothly change across time. Right? As you add, as you go forward in t, that vector field will smoothly change because it becomes more and more Gaussian. Okay, more questions. That's a very good question. So doesn't this mean that this is an ill-posed problem, right? Because if I give you one xt, there could be many possible x0s that originally came from, because there's this noise process, right? So if I start over here right? So I could have started here, and let's say we think about this point, right? So this point could have been created from here with this noise, or it could have been created from here with this noise. And so the difference is that each of these voice vectors has a different probability under this Gaussian process. It's true that there are many possible ways to get to one point, but they all have a different probability. And what this training process will teach our model to learn the average direction that leads back to an original data point. And that averaging will just be the right regularization for things to work. And because it then does it many, many times over across the backward process, the individual average directions will be such small, tiny corrections that it actually still works out. And so this is maybe an important bit here. So maybe in a way, we're not really using a training data set here in the way that you're typically used to in, let's say, discriminative learning for classification, right? There's no one set of pairs of inputs and outputs, x and y, indexed by I. But instead, we have a set of x0s. Those are our draws from that's our data set, the gray thing here in the background. And now during training, every time our data loader comes past this x0, this particular location, the diffusion process that comes in here produces a new noise. It says, I could go from this x0 here. And then the next time the data loader comes by, it says, you can go here as well, and you can go there as well. So that is happening here, right? Within the loss function, new training directions are generated every time we come past. And actually, that's it. So now I can show you some code, and we'll just do 10 minutes of code. So here we've done this, right? So we've got to this point. That was the forward process. And now I need to go back up. And in this class diffusion process, we now also have a thing called backward. That's going to be a function that we will call eventually. That's the magic black box function that takes us back from a Gaussian distribution over time towards the original samples from P0, the actual x0s. And that process is a sequential process. So this is, it's a lot of code, but the main thing to see here is, okay, so this is just storage so that we can make a plot afterwards, right? That's not important. What we do is we discretize the space, and we say we're going to take, you tell me as a user how many steps you want to take to go back from the Gaussian distribution to the original distribution. We initialize at, so if you want to generate, you give me a sample from a Gaussian, that's your x1. We initialize the backward process there. And now you need to give me access to something that estimates this vector field, the model for the learned noise, or the score model, or however you want to call it. It's this thing that minimizes this loss function. Let's say we already had that. Then I can go back in time. So this is what happens here. We go from, this is a slightly unwieldy Python expression, right? We go backwards through the time steps from 1 towards 0. And we always keep pairs of t and t minus 1. And then compute t minus 1 from this update rule that I had on the slide. So for that, we first ask our model to predict what the noise was. So here we evaluate our model, right? So this score is this neural network that will tell us how to get, like, what the direction is. And this is just a little bit of jack-foo to make everything work. That's our estimated noise. Then we can use the estimated noise to estimate what x0 might have been at time t. So that's our pointer backwards towards x0. And then we evaluate this equation that was on the slide. So we evaluate the alpha schedule of our model times x0 plus the direction from x0 to our xt times, so that's this thing, times the schedule for the noise. So that's the square root of 1 minus alpha at t. And so sigma is just square root of 1 minus alpha of t. It's up here. And that's it, right? So this is the mechanical process that we need to call at the end. It's, where is it? So that's this equation, this one here, where we just replaced this x0, xt minus square root of alpha t is x0, we replaced that with the guess for the noise, for what the noise was that got us from here to there. And the only thing left to do is to now have a model that guesses this, that does the guessing for us. And so we'll just train it on a lot of instances of this. Let me go forward again. And for that, we need to do deep learning. So you all know how to do deep learning. We define such a process. We make the plot. We've already looked at that. And now we'll, quote unquote, just do deep learning. So we define some deep neural network. We've already done that when we did Bayesian deep learning. I'm going to define an MLP, a multi-layer perceptron that contains a bunch of layers. This is the Equinox way of writing a multi-layer perceptron. So it gets initialized by randomly initializing the weights of the network, and then it's a set of linear, fully connected layers connected by, in this case, Z-loose, because then the gradients are a bit better behaved. It's a bit smoother, not re-loose, but whatever. We instantiate the model. Done, doesn't cost anything. Now we need to build a data loader. Again, in JAX, building data loaders is a bit annoying, so we use the PyTorch data loader. It's just a standard way of designing a data loader, nothing interesting. And now we make a data set. And here, the data set is also very easy. It's just our 2 moons data sets. So the important thing is here. I'm just saying my data set draws from this 2 moon thing. So they look like these 2 moon samples. And I ignore the class labels because I just want to learn something that looks like 2 moons. I don't want to sample individually from the different classes. If you wanted to have a model, though, that can conditionally sample either one class or another, what would you do? You'd make the class label an input to the neural network. And you say, please learn the score that takes me to a sample from class 1 or from class 2. And maybe I don't just have 2 classes, maybe I have a much more complicated space of images. And this extra input to my neural network is just a string that says, dog in an astronaut suit dancing on the moon. Right? And then that string gets embedded through some word2vec, whatever cool embedding, and gets as an input into my neural network. And my network learns to learn directions that depend on this input string. That's quote unquote the whole thing, right? Okay, now I have a data set, so this is just standard PyTorch. Now we've defined this loss function, that's where the business end is. This is what I had on the slide. So to learn, we tell the model to learn the noise vector that gets us from a particular instance in time, xt, back to x0. And how do we do that? Well, during training, I have an x0, so someone gives me an x0. Then I ask my forward process to make noise at time t. So t gets randomly, uniformly initialized here. That's the line 6. We get a random location in time. I ask the diffusion process, please make a random sample. It tells me that's your random sample xt. I compute the vector between xt and x0. And ask my neural network to learn that vector in an L2 sense. So I return an L2 loss, that's like a slightly nicer way of writing an L2 loss, between the actual direction that gets me from x0 to the noise and the one that the model predicts. Then I just define the loss function, define an optimizer. Apparently, Adam is not cool enough anymore for these kind of models. You need to use AdamW, which is a tiny variant of Adam with just one line changed in the update. And now we can write down a training function, which does the obvious thing. So it runs. I'll let it run actually. Boop. Here we go. A little bit of training. You can see the loss going down. We're at 0.2 over there now. Bloop. Loss has gone down. Initial loss was high. Final loss is low. Looks a bit noisy, but whatever. And now we can make a plot. So you can make two plots. The first one is I can plot the vector field learned by this model. So now I can ask the neural network that I'm going to use in the backward diffusion process, what are those vectors that point back towards x0? And now remember that those vector fields depend on time. At a large time, our distribution will be close to a Gaussian, so all of the vectors just point backwards towards the center. But now, as I go backwards in time, the distribution of this vector field becomes more and more complicated. And close to 0, the model says, yeah, we need to do these final local corrections to get to this two moons model. So this is directly a plot of the neural network that we've learned. It's this score network that learns the noise effectively. And this says, if you are at time 0.1, and you are at any one of these locations, here is what you should probably do to get back to x0. Because if you are at time 0.1, then you're probably very close to the data already, because you've only added a little bit of noise. And so the only thing that really matters is this final shape around here. I mean, out here, it's not a good model particularly, but it doesn't matter because we'll very, very rarely see such cases. And if you are at a large time, at 0.9, 0. Whatever, like at 1 even, well, then just make sure that you're flowing inwards towards the center of the distribution. So now we can hand this deep neural network to our stochastic process, to this diffusion process, and say, please produce some backward simulations. So here I ask my process to run the backward simulation on a bunch of initializations that come from a standard Gaussian. So I just make Gaussian samples. That's my Monte Carlo method now. It's a trivial Monte Carlo method. Just draw samples from a Gaussian, hand those to the network, and say, hand those to the diffusion process and say, please use this learned neural network to take steps backwards in time using 100 steps. And now notice that I can fix how many steps I use here actually, because I now have a continuous model in time. So I've learned a neural network that I can call at any point in time. It just smoothly interpolates along time. So I get to decide post hoc how many steps I'm going to take, 100 in this case, to produce backward samples. And now I just make a plot of those. Here we go. So we initialize with something that's standard Gaussian. And now, so these are the red dots, right? And now I'll let this backward process make this movement for me to push them back towards this two moons distribution. Let's just hope it works, because unfortunately, this code is not quite completely reproducible. I did something wrong somewhere that breaks the Jack's reproducibility. So every time the plot looks a little bit different. And sometimes it doesn't look so good, and then I have to rerun the code. But let's see. And I would say that's decent, right? So now we have samples that don't perfectly come from the true distribution. There's this weird mass lump over here. And maybe it's a little bit lumped out over here. Here, that probably means that the vector field here is not particularly good, and here it's a bit vague. But overall, it's not so bad, right? And now what would be left to do is a lot of engineering, right, to get this to actually work really well. I also have this plot over here. So now someone can come in and spend 3 years and a few $100 million to make this work even better by thinking about a few more things. One interesting aspect that has actually changed things quite a bit, and that happened already in 2021 or so, was to notice that actually what we're doing here is clearly solving a differential equation, right? It seems very pedestrian to think about these individual 100 steps or 1,000 steps that we take. Clearly, the entire process has just a time component, and it's just a continuous thing. And so people had to come up with notations for what this actually means in terms of differential equations. And so here's one of the papers that pointed this out. There's actually various papers from these overlapping set of authors that describe this in different ways. And it's actually quite interesting to look at them. You can sort of see them trying to figure out what the storyline actually is. So here's one of them that sort of emerged from this paper. It says, remember, these are our processes that we had, we used for the discretized version of this process. This is an instance of a discretization, an Ito discretization of a stochastic differential equation. So of the type that we had when we talked about Kalman filters and smoothers, but it's a nonlinear stochastic differential equation. So there is a nonlinear f in front and a nonlinear g. You see that there's a few bold symbols here. So what this means is this x is a set of pixels, right? It's a vector. And that vector changes according to a vector-valued function continuously across time, plus some scalar noise times vector-valued Brownian, times a scalar function times vector-valued Brownian noise. So Wiener measure. There's also an even more general version of this that uses a capital G here, like a vector-valued version of this G, but this is actually probably enough. And so it turns out that there's actually older theory from stochastic analysis, for example, this paper from 1982, that says that such SDEs have a backward process that is actually well defined, and it is given by this equation where t in this equation runs in the other direction, so it runs backwards through time from infinity towards 0. And so this f and the g is the same f and g as up here, but the difference is that you get this score in here. So this gradient of the log probability distribution of x at time t. So that's this local correction that needs to go in, and it's an infinitesimal correction, goes in with dt, right, to make things work. And these expressions look a lot like those correction terms that we had in the discrete time version. And now actually in this paper as well, and then there's a few more papers that point this out, there's an interesting observation, namely that, so this is a stochastic differential equation, so there's a dt here and then a dw, d Wiener measure here. But there's actually a cool theory called a probability flow that works very, very vaguely speaking as follows. So you can write down how under this differential equation, this stochastic differential equation, how samples from this process would move and how their density would change. So if you have infinitely many samples, then their density is given by the probability density function. Right? And then you can think about the change of this density function under this stochastic differential equation, and that change is actually a deterministic object. It's again just the dynamics of a measure of a probability density function moving across time and space. That equation is an ordinary differential equation, and it's this one. So this is neat as an intuition because you can translate this into a more practical algorithm by saying, if I had draws from the original p of x at capital T time, so from the standard Gaussian, then I can apply this ordinary differential equation to those samples, and they will actually do the right thing. And if I had many of those samples, then in distribution, they will do the right thing. Their marginal distribution will always be a draw from the correct distribution. Why is this nice? Because you now get to use an ordinary differential equation solver rather than a stochastic differential equation solver. And ordinary differential equation solvers are much, much more efficient. They are more performant. They're much more studied. They've been studied for 100 years. You know that they're all Kalman filters, but like Mugakuta methods and so on. So you can use these tools now in these so-called stochastic processes, and then they're actually not stochastic anymore. The only stochastic thing you have is this forward process that you use during training of the model. But then during generation, you don't need to do anything stochastic anymore. You just start with a standard Gaussian sample. Okay, that's one stochastic thing, I give you that. But then after that, you just solve an ordinary differential equation. This idea is called flow matching, and it's maybe currently, as of winter 2024, like the hot thing for generating images. There was a tutorial at New Rips last year that was very well attended with like 8,000 people in the room, Ricky Chen telling everyone about flow matching. So this is how you make images. So I asked Google's latest image generation tool to make a picture of how my lecture looks when it ends. Clearly, I need to work on my beard. So this is how effectively all of these models work. But of course, you realize that I've just shown you an example on 2 moons. And this, making images like this requires a lot more work, let alone a lot more GPUs. So nevertheless, it's my best attempt at explaining what happens in these kind of algorithms. I ask for your forgiveness that I have to use something simple like 2 moons. This is a little bit like, we're in an academic setting, and these are models that are now built by teams of hundreds of engineers with access to huge hardware. This is a little bit like if I were a professor for engineering, and this would be a lecture about electrical motors. We might sit here and like wind a few spools and make a very simple electrical motor that just rotates very slowly and in a hacky way. And then I can tell you that that's how an electrical motor works. And obviously, that's not the way that Bosch produces electrical engines for Tesla, but it's the rough idea, right? Similarly, we've now just created a sample from the 2 moons data set by learning a vector field. And if you want to make an image like that, you have to learn the much larger model. If you want to read more about these models, then here's a reading list that is, well, largely comes from Jonathan with a few additions from me, in particular early on. This early paper by Apo Hivarinen from 2005 is maybe like the first idea for this noising and denoising score matching step that I know of. There's probably an even older one that I haven't seen. And then many of these different papers that developed these ideas over the years. I can also recommend, actually this blog post is quite nice, has a lot of nice visualizations. And also there is this tutorial by Ricky Chen and 2 other people at New Rips last year that I got to walk through, and then I didn't have time because I needed to meet a few people, but it's actually quite nice. It's been recorded, you can watch the videos, and they have a lot of examples. This is a tutorial by Meta for their own generative model, and they have a GitHub repo that contains some tutorial examples of how to train flow matching models, so the ones that are based on these ODEs ideas. And also, thanks a lot, and once again, to Jonathan for helping me also write this piece of code and make it work. I fixed the last bug this morning. Well, I think it's the last bug. Obviously, it's not the last bug. If you find more, let me know. So here's the summary. We got towards this idea by starting out from Monte Carlo methods, which I introduced on Tuesday, noticing that sampling from a distribution is hard when it has a complicated geometric shape. So there's a really cool idea that says, let's take a sample from a distribution, add a little bit of noise to it, then it'll come from a distribution that's easier to sample from. And then we can take a step backwards towards the original distribution by estimating, using Bayes' theorem, what the original sample may have been if we draw from the smoother distribution and want to go back to the more peaky distribution. That step involves the score, the gradient of the log probability distribution at that point in the sampling process. And then we notice that if you do this in one step, it can be a dangerous process that has a lot of noise, a lot of uncertainty, sorry, not noise, a lot of uncertainty in the estimate. So the trick to get out of this is to not do one noising step, but a lot of them. In fact, a very large, asymptotically infinitely many infinitesimal steps to smoothly move from a general probability distribution towards a standard Gaussian distribution. And then the backward process is the solution of first an SDE, but in distribution it's actually an ODE, a flow, that you can solve with an ordinary differential equation solver. And the only ingredient you need is a model that estimates what the flow is at each point in time and in space. And that model can be trained, for example, as a deep neural network, but of course you could also use a Gaussian process if you like, right? It's just a regression problem. By drawing samples from an initial distribution and then asking the forward process to create an instance of a sample from the forward process and training the network to minimize L2 loss on such samples. By now, these models are commonplace. They're used to generate images, videos, but also increasingly other things like the dynamics of proteins or weather forecastings, nowcasting, and so on. There are also variants of these processes that don't diffuse towards a Gaussian, but they diffuse towards a binary 0-1 distribution. You can imagine that there can maybe be a similar thing where you noise with Bernoulli noise with a certain probability that gets increasingly larger as you go towards 1. and then you end up with like random uniform bits that you initialize from, and then you can go backwards. I think that's going to be super interesting for theoretical computer science if you're of that sort of persuasion, how to draw from the uniform distribution over all binary strings towards a distribution over workable programs on a Turing machine. So the story is just beginning. There'll be a lot more on this, and it's fundamentally a very probabilistic process. That ends the section on random numbers and their use in the generation of samples from arbitrary distribution. Next Tuesday, I'll move towards a third way of approximately computing posterior distributions called variational inference. Thank you.